I need to introduce you to a couple of differential equations. Now, don't get nervous. We're going to get through the differential equation part pretty quickly, but we need to use those differential equations, and we will use those differential equations to be able to quantify changes in entropy, delta little s, particularly for ideal gases. So let's see where we're headed on that. This little module, I totally talk about these what's called TDS equations that are going to be two differential equations. It turns out they're going to be powerful, and then we will use them sort of as a result. So we're up to section 6.3 in your textbook, and the textbook does a good job, a far better job than I could do, of deriving these two differential equations. And what they do is they relate six intensive thermodynamic properties to one another. And so what? What's the purpose of that? It's going to give us a computational method to determine entropy change. So remember, what we're going to be trying to do in this chapter is going through a process, say 1 to 2. We want to quantify what is S2 minus S1. And we're going to be able to use these differential equations when we have the substance ideal gas like air, nitrogen, CO2, argon, you name it. So in section 6.3, the textbook introduces these TDS equations, and it starts in its derivation with this familiar looking expression for incremental change in entropy, capital S. It's del Q over T, as long as you undergo a reversible process. Now, we're going to get some kind of neat results about this, but I'm going to skip right to the bottom line. So rather than going through this derivation, I'm going to say, let's say a mathematical and engineering miracle occurs, and we end up with equation 6.8, which is called the first TDS equation. And so let me just read it out loud. TDS, where we've got capital S, is equal to D capital U plus P dV. So do you see why it is a differential equation? We've got this incremental change in capital S, this incremental change in volume, and incremental change in internal energy. So for this video, we're going to use this as sort of given. To get to the derivation, you got to go to your textbook. The textbook then goes through the definition of enthalpy. Do you remember what the definition of enthalpy is? H? Well, it's up here in the screenshot. H is U plus P times V. H is U plus PV. That's purely the definition of H. And why did we come up with that? Other than, well, what we did was we find that we use enthalpy a lot when we have open systems, because in open systems, we had a term called flow work. And to make our lives a little easier, we start using H instead of internal energy U. So U includes the flow work term PV. Well, anyway, the second TDS equation can be derived by taking the first TDS equation and substituting in the definition of enthalpy, and you get the second one, T times ds equals dH minus V dP. So this is a second differential equation. All right, so you got that? I hope your head's not spinning, because we're kind of getting near the finish line here. Now, in our class, and in our case, we're going to be using these two differential equations on a per mass basis. And so we divide both of the equations, both of the left-hand side and the right-hand side, by m, the mass of a system. All right. And so now we get the two TDS equations that we will be using to our advantage in a subsequent video. And here it is: T times D little s equals du plus P d little v, and Td little s is dH minus V d little p. Okay. And so the important part about this, so an important part for me to make, that the textbook also makes is that this enables us to quantify changes in entropy without going through some tedious integral between states 1 and 2 for reversible processes, even if our process is irreversible. So the differential equation is an expression of the relationship of 6 variables that do not depend on the path. That's going to be a big time saver for us. So in other words, these two expressions are path independent. A little bit more on that in just a short time. Let's do a units check. Before I make some conclusions, let's do a little bit of a unit check. So I've written out my two differential equations, and what I'd like to do is let's look at this bottom expression, and let's do a units check on this. Be sure the units are consistent. T, well, that's degrees K. ds, in the previous video, I said d little s has units of kilojoules per kilogram, degree K. Degrees K is in the denominator. Okay, so let's see can we cancel stuff out? Yeah. So the left-hand side is going to have units of kilojoule per kilogram. All right, well, let's look at the right-hand side. DH, incremental change in enthalpy. Well, enthalpy has units of kilojoules per kilogram. So far, so good. We're uniform. And then if we kind of combine visually our two equations, we've got a plus term and a minus term. But let's look at the units of little v, meters cubed per kilogram, okay, dP. I've got to have my pressure in SI. My pressure's got to be in kilonewtons per square meter. What is that? That's a kPa, pressure in kPa. And let's see let's see, I've got meters cubed up here, meter squared down there. So I've got a meter times a kilonewton meter. That's a kilojoule, and a kilogram down here. Great. So we are consistent in our units, kilojoules per kilogram, left-hand side, right-hand side of our TDS equations. Let's do the same thing with the English units. Okay. Left-hand side, TDS, we've got degrees R, and so units of entropy, little s, BTUs per pound mass degree R. So left-hand side, good, BTUs per pound, compare it to DH, enthalpy, BTUs per pound. So far, we're consistent. And let's do the same thing with VDP. V is going to be cubic feet per pound mass. Pressure. Now, let's look at this real carefully. Look at this pressure. It's not pounds per square inch. It is pounds force per square foot. So that's something to be mindful of when we're problem solving. Pressure, pounds per square foot. But also, look here. I've got pounds force per pound mass. That's not a BTU per pound. So I've got to remember my conversion. There's 778 foot-pounds force in 1 BTU. So I'm going to write this out in my second term. 1 BTU in the numerator, 770 foot-pounds force in the denominator, 778. I might have said 770. All right. Let's do a units check. Pounds force cancels with pound force. Okay. I've got cubic feet here, and now I've got cubic feet here to cancel. So I've got units of BTUs per pound mass. I am consistent with my units, but do check. Don't forget. Look at how I'm dealing with my pressure in English. I'm converting pressure to pounds per square foot. Some comments about these two differential equations, and to try to make you feel better about this particular course, we're going to integrate those two differential equations, and we're going to get to a working result quickly. We don't have to worry about doing the tortuous math of solving differential equations. However, if you're thinking about graduate school, and I encourage you to do so, if you're thinking about staying for graduate school or going to a different graduate school than Virginia Tech, I think that is a wonderful idea. I highly encourage it if you enjoy working with differential equations. And so, for example, if you find these interesting and you find the mathematics interesting, that's a good signal that you may be interested in hanging around for a master's. Okay, so recognize there's plenty of first-class mechanical engineering graduate school alternatives, and Virginia Tech is one of them. I highly recommend it. I greatly enjoyed and benefited from my master's level graduate school experience at Virginia Tech. But if you find this differential equation mathematical solving interesting, graduate school is something to consider. We've come to the recap, okay? And the recap is simply stating these two differential equations. You should not have to commit them to memory until you get to graduate school, okay? But let's see what they do. These are two powerful differential equations, and what do? They relate 6 intensive properties to one another. So let's look at the properties. T, that's 1. S, 2. H, 3. U, 4. V, 5. And P, 6. And so it's a very interesting study in differential equations where we have two equations that relate 6 intensive properties to one another, and it takes away this having to integrate across reversible path. And that's the big conclusion. You say, okay, well, where are my numbers? The statement of the TDS equations is powerful enough and important enough just to have in one video. And so in the next video, I'm going to show you how to use those TDS equations to derive some very powerful results for ideal gases. So I hope that helps. I hope that did more than just totally confuse you. But the TDS equations are an important part of this course, and certainly an important part of graduate level thermodynamics as well.